All right, so I'm John Levering. I work for Precision AI. I took all my swag off. And I'm going to talk to you a little bit today about Cutter and Frida, which are decompilation and code injection tools. So the theme of this talk is debugging code you don't have, and I'll talk a little bit about that. First, maybe a little who am I? So for those of you that don't know me, I spent 10 years doing firmware development in San Francisco. I worked for a couple of companies you might have heard of. And I'm currently the head or the embedded systems lead at Precision AI. Joey told me I needed to pitch my company really hard during this conversation. So, no, I have a couple of slides just because you might not have heard of who Precision is. So Precision AI, our goal is precision agriculture. We're building a drone platform that can do precision application of herbicide to only weeds within the crop. So this is a marketing slide that my CEO gave me. So there you go. Basically, we use cameras, machine learning, a drone, and then a spray platform. Our goal is to fly over a field, see a weed, and deliver herbicide to only that weed. There's some studies that say that up to 80% of what a farmer sprays when they use a traditional high clearance doesn't hit what they want. Our goal is to converge that down to only hitting what they want. There you go, that's my whole pitch. So back to my actual presentation. So this is about reverse engineering. Why do we reverse engineer? The biggest thing that this comes about from is understanding code that we didn't have. It had some bad behaviors, some bugs that were really confusing to us, and we wanted to identify what those are. Anybody that's ever worked in an SDK vendor relationship will know that as soon as you tell your vendor, hey, you have a bug here, their first answer is, no, you're using it wrong, go away. So a lot of this was about being able to identify exactly what the bug was so we could really clearly show them that they had a bug. And also to see if we could mitigate the bugs in their SDK without needing to actually try to make them move, because that's a unstoppable force hits an immovable object kind of situation. We used basically two tools in this process. The first one I'm going to talk about in a little bit more depth, which is Cutter. Cutter is a nice graphical UI based off an open source tool that uses Gerdia, which is a decompiler thanks to the NSA. It can take an arbitrary library or binary, and it can give you the decompiled symbols as best it can. Decompilers have existed for a really long time. This is a really nice way to actually use a decompiler. As you will see, I'm going to have some screen caps. What you get out of a decompiler is not pretty code like you wrote. You get a lot of garbage and trash, and there's a lot of things you have to do in order to start figuring it out. The other tool that I'm going to touch on, I don't know if I have the time to kind of dig into it. It's called Frida. This is actually a code injection framework. It strangely works in JavaScript. It's an entire JavaScript API layer that gives you the ability to kind of go into code and instrument calls, instrument sites within that code, replace calls within that code, so you can actually take a function out of a library and replace it with a different function call. So it's extremely powerful. And yeah, it runs as sort of this JavaScript API, which you can write all kinds of fun little scripts for. So the way I've chosen to do this is to take you on a journey through how I went about doing this for a specific problem we were trying to solve. I've obscured the names to protect the identities of the guilty, which means I'm not going to actually talk about the name of our vendor, the type of hardware we're talking about. I do ask that if I have missed that somewhere, that please don't, take that and shout that on all your social medias. I've tried really hard to not identify the vendor. It's not actually super important to the process, and I'm not trying to shame them, except for the one slide where I definitely try to shame them. So a little bit of the context of what this came out of. So as I said, we have a system. It's got hardware, it's got cameras, it's got sensors, it's got GPS sensors. Eventually, it'll have sprayer hardware. It's got a lot of pieces of hardware. We didn't build all of that hardware. We didn't write the code for all of that hardware first. So for a lot of it, we have these vendor SDKs. In this particular example, we have a piece of hardware that was randomly failing. And after it would fail, it would look just fine. It had no errors. It had nothing we could identify. You could immediately connect to it and start using it again. So that was really odd. We knew from its data sheet that its SDK establishes this heartbeat mechanism between them. And if the heartbeat failed for some reason, that's what the device would be expected to do. It would just reset to its base state and expect you to connect again. So we had a suspicion that the heartbeat code as written by the vendor probably had some edge cases where it would just randomly fail and stop sending heartbeats. And we wanted to get into understanding what that was really doing. They, of course, didn't think their code was wrong. When asked, is there any cases this can fail, they were like, no, it's perfect, just go away. Which obviously wasn't helpful to us when we knew it was definitely failing in some ways. So what I decided to do, or what we decided to do, was dig into it, go and investigate the code, see what we could find out about how the heartbeat actually works within the SDK, and then see if we could fix it in some way to at least prove that that's what was broken, or at least instrument it so we could prove that that's what broke when we saw these other artifacts. So I'm going to break this down into sort of 3 steps of the process. Now I've sanitized this. The way I did this was more of a zigzaggy circular line going all over the place. This is the way that if I had the benefit of telling myself now, I would tell myself to do it. So step 1 being sort of identifying code paths that are interesting. Step 2, figuring out what the code is actually doing. That's going to make more sense once you see what decompiled code looks like. And then step 3, validating that by instrumenting the code. This is where the Frida part comes in. So yeah, step 1, collect the underpants. No South Park reference? Oh boy, I'm showing my age now. This is going to show up a few times, so oh well. So identifying the interesting code paths. Over here is a picture of what you get when you open something in Cutter. You go in, you load a library. It has this really neat little interface where it'll ask you a ton of questions about how much work you want it to do to try to figure things out for you. If any of you are actually going to do this, the defaults work really well, and you should only add things if you're pretty sure that you need them, which means going and reading the documentation. I'm not going to try and succinct the like 3,000 pages of documentation here. But what's sort of really useful is once you get something loaded, you can't read this on my display, but on the left side, there's all of these things that say fnc.xxxxx. Those are what it understands to be symbols. When you get a function in a decompiler, it doesn't know what the function was called unless the library itself was exporting that symbol. So anything that you could link to with that library and call, you'll have a symbol for. If it's something that's only used within the library, it gets an alias. So you don't actually know what it's called. So what Cutter does is actually label them according to the memory address they're found within the SO. So that's where the XXX comes from. There's a thing that's not shown here, but if you actually do jump into this and you open a library, sometimes symbols show in blue. That means they are aliased to something that came in from a different SO. So it's you have a multiple link situation, and it actually has tools to tell you all of the libraries it depends on, and you can get that. Now, in our particular case, the symbols we cared about were provided by another library from the first library we actually link against, which means they actually had names that were useful once we went to that library. If you are doing this on a more closed library, you might have more problems of you're going to have to probably start from the beginning of time and work forward to figure out what things are. And it's a lot more work, but that's probably the only way you're going to be able to do that. So this is what it looked like once I filtered for symbols that contained the word heartbeat. So all of these look pretty promising. Again, I thought this image was clearer, that's why I recaptured it. But I'll go through what those say sort of here. These are the symbols that we find. There's a do thread stop, there's a thread running, there's a heartbeat callback, there's a C heartbeat thread, an underscore C heartbeat thread. The symbols aren't going to have tildes in them, so we're going to guess that that's probably the constructor-destructor pair. And then we have start heartbeat and stop heartbeat. One thing I failed to mention is that most of our code is in C++, so this is a C++ native library. So we're dealing with C++ style objects. All right, so we've identified some interesting places. So step 2. No joke, okay. Come on. So now what we want to do is go through and do some analysis on these different code paths. So I mentioned we have this sort of pair of heartbeat and underscore heartbeat thread. I typed threat, so you know, I'm not perfect. And then we have this pair of start and stop. Those are kind of interesting. And then we have thread running. I've omitted the do thread stop, but I will visit it briefly as we go through. So now we're trying to understand, what does this object look like? What do these code paths do? How do they function? So we go and we look at those code paths. Oh boy, I really wish I'd made those images bigger. So this is the constructor. This is how it deconstructs. It does not look like real code. You have a mangled name at the top, which thankfully Cutter demangled for us, which was nice of it. You can see there's a function call. There's a really obscure argument typecasting, another function call, some more like weird offset assignments, and other things. So what we can start to understand about this is we're pretty sure we're in a C++ object. That first thing, that first function, we'd probably guess that's like a call to the superclass constructor because it takes the base pointer of the object. I actually did verify that. It's not shown, but you can go through and it looks very much like that. The next kind of line there where it has that arg assignment and it says vtable for, that's actually really interesting because that's how it's getting the C++ vtable into the object space so that you can actually use it. It's a pointer to a place where it'll find the vtable. The next part is a function that takes that base address of the object and some offset. And that's kind of interesting because that means it's being passed something that's within the object. So I tunneled into that and I was like, what is it? And that one you can actually read. And it's calling clib libraries. It's initializing a condition variable and initializing a mutex. So what we now know is that at offset 18 inside the object, there's a condition variable because it's that offset 0 inside the call. And then the offset 30 from that, there's a mutex. So that's interesting. And then there's also some other thing that gets initialized at offset 60 to 0. So we write all that down, or we remember it. And then there's some other stuff that's getting initialized to passed-in variables. There's an interesting thing at 0x88 that just gets set to 0. So we're like, okay, there's something there that's some kind of value of some kind that might be interesting. So then we go on, yeah, I don't mention the destructor. The destructor is kind of also the same thing, but in reverse. It calls some function that deconstructs the p threads. So now we're going to look at our next pair, which is our start and stop heartbeat, because they're also kind of interesting. So when we start the heartbeat, we see that at some offset 88, we're setting that to 1. And then we call this magic function with plus 18, which we know was the address of the condition variable. So we go in there and we take a look at that. We see that it locks the mutex, sets this other flag at 0x6 to 1, then it unlocks the mutex, and then it signals. So this is kind of, if you've done condition variable signaling, this is a pretty normal kind of pattern. You're setting some kind of flag and then you're signaling. The 0x60 flag part is just telling it that in fact was a signal to the condition variable. This is important because if you go and read the man page for a condition variable, it will tell you that anything that's waiting is not guaranteed to only wake up when signaled. It can wake up at any time the kernel so desires it to wake up. So it's a really common pattern for you to actually put a flag in there to tell whatever is waking up that actually you did intend it to wake up, otherwise it can go back to sleep. When we look at the stop, we see that it clears that 88, and then it calls that signaling function again. So pretty common. We can now surmise kind of that 88 has some significance to the internals of this. It tells it basically to start or stop. We might think that it's like an enable for the thread itself. And we know that we have these condition and mutexes. So we'll take a brief jump into the do thread stop, and you have no idea how many times I had to rework my presentation to turn that into 2 C++. So just fun. This is, I thought, really interesting for C++ nerds, because this is what a trip through the C++ object vtable looks like. On the left-hand side, my left, I guess it's your left too, the far side, you have what the decompiled with symbols looks like, and they're pretty innocuous. On the right, we have the actual disassembler. This is ARM64, so I'm going to give you a quick crash course in ARM assembler. These are the functions that or the instructions you're going to see: store pair of registers, load pair of registers, move between two registers, store to a memory location, load from a memory location, branch and link, which is a really interesting one for this example, and branch. Branch and link is when you are going to come back to where you called the function from. Branch is when you're just going there and you don't need the processor to know where to come back to. Usually a branch and link has like stack frame pushing and all of that other magic, if you remember from operating systems. Nop, don't do anything. Used as a verb, that guy's a nop. You can add that one to when you're making fun of your coworkers, and then add, which is addition. So if we come back here and we look at the disassembly, we can see that this innocuous function call on the left for the first one is actually a bunch of stuff going on. Even though I just talked about all of these functions, we actually don't really need to go through them that much. What we kind of know from this is that's just preparing the stack and the registers for the function call. So this is just doing whatever the ABI for C++ requires in terms of passing by value, passing in the memories in the stack, passing in registers. So it's putting a bunch of stuff in stack space and loading things into stack space, and then it does a branch and link. It then goes to this other function, and this is where the magic through the vtable happens, is this bottom function. What it does is it's going and finding the actual program space definitions, and that's where the ADRP X16, I don't know if I put that in my crash course. It's a really confusing one, but basically it is a load this register with a value that is a program counter offset. It's a really weird thing, but basically it ends up with something that you could jump to. That's the end there, and that's the base of the table. Then it does some loading with offsets to get the correct function pointer out of that table, does some adds to get that to the right place, and then it branches to them. And so there's a really neat kind of little flow here where the branch and link says come back here, and then you do some like magic to get the correct place in this register X17, and then you just jump there. And that's how you end up in the function that belongs to your object. Because, and I don't know if this is an operating systems class or anything you would have covered in that, but the functions themselves only exist one time in program memory, so and then they're just called. It's actually, they don't live actually on the object like we always think about with object-oriented programming. Yeah. So now we're at the meat of it, the thread running. And what does this thread actually do? This is a great example of how decompiled output looks nothing like code you would write. But we can get an idea of what's happening here. It checks something at offset 8 to see if it's, as long as it's not null. So this loop will keep going as long as that value is not null. We then call some function at 0x18. We remember that's the condition variable. And then it gives it some arbitrary constant of 1,000. And then we check whether or not 0x88 is set, not null. They use /0 here. For some reason, the compiler thought that was more clear than a 0, or the decompiler. And then if that is true, we do some action that lives inside this, this FNC 00111B0. We can dig into that. Again, it's a trip through the V table. It's kind of neat. But you end up with this function that's read register little endian. So we're pretty sure at that point that's actually going out and talking to the hardware device. And we don't have any reason to believe that's broken, so we actually don't analyze that much further. But it does kind of tell us what offset 80 is within this object, because we can kind of infer that that's a pointer to the object that controls the physical interface layer. The HAL layer is what we would say. And then OXA00 is some kind of magic instruction to the device. So this FCN 00114A0 is probably an interesting function to look at. We know it's operating on the condition variable. So, so what's that doing? So this is the slide where I shame the vendor. When I actually went through to capture these images, I used a newer version of the library, and I realized this is not what I found the first time I did it. So the top is the original version, and the bottom is the new version, and it's going to be quiz time. Does anybody know why the top version is broken? Anybody? I'll give you a second. All right, I'll go through it. It's a subtlety of programming, and it actually comes back to that pthread condition time wait. If you go and look up the pthread man page, it will tell you that it must be called on a condition variable that is initialized with a mutex that is locked. So when it gets called on param1 and param1 plus 30. We know plus 30 is where that mutex lives. But we've gone through all of the function calls here. We never saw a call to lock mutex. So when this is called, this mutex at OX30 is not guaranteed to be locked. So if you go and you actually look at the man page and you say what happens if you call it with an unlocked mutex, it will say this is a strictly undefined behavior. We don't know what will happen. Your code might crash. Your code might behave erratically. It might immediately return. It might never return. We make no promises if you call it in this way. So we don't know if that's the bug, but we know that that's definitely wrong. And what's very interesting is when I went back, if you look at the very top there, the first thing they now do is lock the mutex. Then they check that it's locked, and they do some other stuff. The rest of this function is just shoving that 1,000 into a get time of day struct. If you look at condition time wait, it takes a absolute world time, and so they have to kind of compute this 1,000 milliseconds in the future or 1,000 microseconds in the future and they have to ask the system to give them a time of day, and that's what they're doing here. And the rest of it is just kind of going through, doing that, but you now see that in the revised version, they actually correctly lock the mutex. So now it actually has defined behavior, and the wait will either return at its elapsed time or when the signal has happened, and not in some other random unknown way. Which was kind of the point of this exercise, if you remember back, was to find, hey, is there some weird bug in their code? And it turns out, yeah, there's some weird bug in their code, which they then fixed, and actually most of the bugs went away. So I'm fairly confident that this, in fact, was the problem. I didn't actually. They told us that this is this gets a little bit off in the weeds, but for reasons of stability, we had to stay on the older SDK on the particular thing we were testing. Everybody that's worked in a startup will know that we were racing towards a demo, and the last thing you do when you're racing towards the demo is rev your critical hardware libraries. So we weren't in a position to rev this library, but they already had this new version out, and they were like, oh, just test with the new version. Of course, they didn't say, because we were brutally miscalling POSIX code, and there was no way it was ever going to work properly. But there you have it. So to summarize kind of what we learned, because I threw a lot of numbers out there, we got a really good understanding of what the structure is. These are kind of all the memory locations we found and what we know is there, you know, when we actually know it's there. We still have two variables that get passed into this at construction time that never get called anywhere, so we don't really have any understanding of what they are, the ones at OX90 and OX98. They're pointers, we're pretty sure, because they get passed in as like int64t, which on a 64-bit system is generally what your pointer size is. So we're pretty sure there's some pointer magic going on there. There's some other hardware things that they thought they might need, or the parent class uses that is not a functionality that this class is using. So that's kind of interesting. And then the other summary point there is we found this potentially really bad bug. So then step 3, profit. Still just a dead joke. I promise I'll use better memes next time, or at least ones that are more fresh. So step 3 is what can we actually do with this information? So this is where the second tool comes in, Frida. We want to be able to test our assumptions before the vendor releases a new library that we can go and actually look at. At the time, I only had what I suspected was broken code. So we want to be able to go in and instrument when the heartbeat is actually firing. And that's what Frida allows us to do. We can actually build a way to log when that code is getting run within the other code. And then we can run it, get to the situation where the bug occurs, and see that it actually stopped. And be like, oh, okay, we have a pretty clear idea that that's what happened. I haven't gone into a lot of detail. Frida is an amazingly powerful framework, and if you actually need to do this, go and read its documentation. But here's another old reference. So we're going to go in and we're going to just intercept that heartbeat action. And we can actually do this all from JavaScript. So we write this little thing that says find the module, which we have the module's libname, and then we use the memory offset that we can get from Cutter. We can go, hey, where's the function getting called? This is the action function that was actually taking that write hardware register action. We can grab its memory address, put it in here. What we get back is this like some magic object in Frida that tells it that this is a spotting code. We can then tell it, make an interceptor that attaches to that spot, and when that spot gets hit, call this other function before you execute that. So on enter, it's going to call this function, and we just do a send, which prints out to Frida's console, oh, I intercepted the heartbeat. And then we can run the code, and every time it fires, we get this printout on the Frida console. One thing that's really neat about Frida is you can actually embed it into your own application. You can load it as a dlib at start. It either attaches like GDB, you can attach it to a running process, or you can like load it at start and then give it a scripts directory, and it will run those scripts on start. So you can actually make this a little bit more streamlined. But this allows us to instrument and see, yeah, it is in fact stopping. And now you always have a problem when you do something like this, which is, did it stop because it was the bug, or did it stop because I'm using a weird code injection framework to inject JavaScript into my native application and a time-critical process, and maybe that actually caused it to crash? So what this doesn't really allow you to do is take your console log back to the vendor and say like, hey, your code is broken, because they're going to be like, what is this, and why are you trying to reverse engineer our code? But then maybe we want to do something a little bit more exotic. Maybe we want to completely replace that action, or replace this code that we think is bad. So this is how you would go about doing that. This actually now uses native code injection, so we write the functions that we're going to use in the application itself, and then we just use Frida to kind of massage the function pointers within the application as it runs. So on the right-hand side, these are the functions I wrote. The artificial heartbeat is a direct copy of the actual heartbeat that runs. And then there's a placeholder, because we still want to call the original action. We just want to run our heartbeat code. So, so there's a special placeholder function that looks exactly the same as what is happening in the original code. And then what we do is we locate the original call to heartbeat. This is the original call to thread running, and we replace it with our artificial heartbeat code. So now when that function gets called, it's actually going to run this code. And this is native code, so it'll run fast. So that happens one time. It's actually not too bad. That's what the interceptor replace does. The rest of this is just magic for Frida to massage the symbols into the right thing. We can actually look the symbol up by name in this case because I compiled the code, so I have symbols. So I can actually tell it to find it in the debug symbols. And then the next part is that placeholder. I don't actually want to do nothing. I want this to still work. So I go and I find that placeholder in my code, and I actually find the original action function call within the memory stack, and I replace those. So now when you get to this artificial heartbeat real call placeholder, it gets replaced with the actual real call. So this is now exactly the same as the original, and this actually worked. Or put maybe another way, I heard you like code injection, so I put some code injection in your code injection. At least that one got a laugh. Whew. All right, and that's my story about using Frida and Cutter to do analysis. So yeah, I'll take questions. Try to keep that as high level as possible. Sure. How long did it take to go through that process? Well, I was working on fixing that bug full time, so it probably took me only about 3 or 4 days to go through that process, but like full time, and figuring out a lot of things. So yeah. Other questions? Nobody? No, we don't. Well, okay, I'm lying. We have LiDAR. We have a LiDAR sensor. So technically it has a laser. Anybody else? No? Precision AI questions? Sure. Oh, physics. Yeah, so the question is why the switch from the quadcopter to the fixed wing? And the answer is physics. Specifically, range endurance and lift capacity. So as we move to a spray solution, you're talking about carrying tens or more kilos of weight. And in order to do that on a quadcopter, that means adding more battery, which is more weight, which is the rocket problem. And eventually you get to a point where you're either building, autonomous helicopters, or it actually makes sense to lift things with fixed wings because they're actually more efficient in that domain. So in order to hit our goals, which is to be competitive with existing products in the marketplace, such as high clearance sprayers, we have to be able to cover a certain amount of terrain in a certain amount of time, and that means we have to go a certain speed and last a certain amount of time. And so, yeah, it just became sort of necessary for us to move that direction. It creates some more interesting problems in my part of the world because now we're moving faster. A quadcopter can fly comfortably at 0 to, whatever speed is its max speed. A fixed-wing aircraft must fly at a minimum speed. If it flies slower, it falls out of the sky. It stops being an aircraft. So that's a limitation, but that means that our time from image capture to when we actually have to act on that image is now necessarily predicated on how fast the drone is flying. So yeah, hopefully that answers that question. Other questions? If not, I'll give the microphone back. Awesome.